Hi everyone, and welcome to the inaugural seminar for the Mathematics in Higher Physics of this year at Physics Latam. Today we are truly honored and more than happy to have Professor Edward Witten opening this seminar series for this year. And as you well know, he is one of the world's foremost experts in mathematics and higher physics, making him the perfect choice to kick off this seminar series. Today he's gonna talk and give an overview to algebras in field theory and gravity. Edward needs no introduction, as he is a legend in both in physics and mathematics. However, in keeping with our tradition to introduce every speaker, we will give a brief introduction. He is a renowned theoretical physicist, known for his contribution to string theory, quantum field theory, mathematical physics, and pure mathematics. After receiving his PhD from Princeton University, Witten became a junior fellow in the Harvard Society of Fellows and later held an appointment at Princeton University. In 1987, he joined the Institute for Advanced Study, where he has remained ever since. Witten's work has significant influence topics such as string theory, quantum gravity, supersymmetric quantum field theories, topology, geometry, and many others, bringing the gap between physics and pure mathematics. He was the first physicist awarded with the Fields Medal in 1990, recognizing his proof of the positive energy theorem in general relativity and his interpretation of the Jones invariance of knots as Feynman's integral. His other accolades include the Dirac Medal, the Crawford Prize, the Lawrence Medal, the Breakthrough Prize, and the Basic Science Lifetime Award, and many other prizes. The list is very long. In 2004, he was listed among the top, among the Times Magazine 100 most influential people. We will take questions at the end of this talk. And once again, we are very happy to have Edward Witten with us. Please, Edward, go ahead.
Thank you. So, as we know, quantum mechanics textbooks usually consider an isolated system viewed from the outside by the observer. However, as observers in the universe, we're in a different situation. We're part of the system that we are trying to observe. Now, we can't expect to resolve the quantum microstate of the whole universe, partly because it would be impractical, but also in principle because we cannot see beyond the cosmological horizon. So some of textbook quantum mechanics does not quite apply. I'm going to assume, though, that some of textbook quantum mechanics does apply. I assume that first, observables form an algebra A, meaning a vector space with associative multiplication. Second, I assume this algebra has an operation of Hermitian conjugation. And third, I assume what we're measuring can be viewed as expectation values of observables in the state of the universe, however the state of the universe is described. Finally, more technically, I assume that positive observables have positive expectation values, meaning that if A denotes the expectation value of an observable in the quantum state of the universe, then for all A, we'd like the expectation value of A dagger A to be positive. That's actually enough to imply via something called the GNS construction that observables can be viewed as operators on a Hilbert space, just as in standard quantum mechanics. Formally, we introduce a symbol psi equals psi1 that represents the presumed state of the universe. And for any A, we introduce a symbol psi A that represents A psi. In other words, it represents the state of the universe after acting with A. Inner products are defined by saying that the inner product of psi A and psi B is the expectation value of A dagger B for any two observables A and B. Because of the positivity assumption, this definition is consistent with all inequalities expected for inner products of Hilbert space vectors. So after dividing by null vectors to get a pre-Hilbert space and taking a completion to get a Hilbert space, we arrive at a Hilbert space H that provides an arena for any observations we may make. That doesn't mean that H describes the quantum state of the whole universe. It was defined with no knowledge of what's beyond our horizon, so it contains no information about anything beyond the horizon. Since we can see distant galaxies, the action of our observable algebra A on H contains information about those distant galaxies, but it does not contain information about anything beyond our horizon. Even from a complete knowledge of the action of A on H, which of course is highly idealized compared to what we actually can learn from observation, we wouldn't expect to learn anything of what's beyond the horizon. So there's a proposal, technically, that's relevant here, but it requires some knowledge of what's beyond the horizon. What kind of algebra is the algebra A of observables accessible to us? To get a simple answer, we need two more steps. First, to get a simple answer, we assume what we regard as observables are bounded operators. A mathematical reason for this assumption is that bounded operators can be multiplied and form an algebra. By contrast, to multiply unbounded operators is problematical. A physical reason is that in practice, our measurements are valid in bounded ranges. So for instance, when we measure the electric field, we can only resolve values in a bounded range. So in effect, we're measuring a bounded function of the electric field. So beyond what I said here, which is considering bounded operators, we need one more step to get a simple structure theorem for the algebra. This is that B, roughly, we don't try to distinguish operators that can't be distinguished by experiments. More precisely, consider a sequence of operators A1, A2, and so on, such that for all states psi and chi, the limits of the matrix elements exist. If that's true, we define an operator A, whose matrix elements are given by those limits. And we say that A is the limit of the ANs. Mathematically, this is called a weak limit. We include such limits on the grounds that an experiment measures finitely many matrix elements with finite precision. So under the hypothesis I stated, any given experiment cannot distinguish A from AN if N is sufficiently large. In other words, from an experimental point of view, the statement is true. So we just declare that it's true mathematically. Finally, although this is more subtle, physically it's well motivated to expect that the center of A consists only of complex scalars. To be more precise, this assumption seems well motivated in a closed universe. In an open universe, if the observable region goes off to spatial infinity, one may need to modify this assumption to take conserved gauge charges into account. Now, the points A and B with bounded operators and limits make A what's called a von Neumann algebra, and C, where the center consists only of scalars, makes it a factor, the analog for algebras, of a simple as opposed to semi-simple Lie group. Such algebras have a simple threefold classification. A complete classification given a further property of hyperfiniteness, which holds in quantum field theory. If A has no simplifying property beyond what we've assumed, it's said to be of type 3. If our observations are described by a type 3 algebra, that means there are no simplifying properties beyond being able to define probabilities. There actually are theorems showing that out of all von Neumann algebras that act on a given Hilbert space H, the generic one is of type 3. So these authors proved one version of this statement. That's natural. It says that any significant simplification beyond the axioms is non-generic. Well, what kind of simplification might you be interested in? There are two important types of simplification. And if the algebra has one of them, it's said to be of type 2 or type 1. If the algebra has a trace but no irreducible representation, it's said to be of type 2. If it has an irreducible representation, it's said to be of type 1. By a trace, we just mean a complex-valued linear function that has the usual properties of the trace. The usual properties of a trace are this one, trace AB equals trace BA, and also positivity. The trace of A dagger A is positive for all A. To get a type 2 algebra, we don't just require that the trace is defined and finite for all elements of the algebra, only for a sufficiently large, dense subset. For a type 2 algebra, the function trace is not a trace in a Hilbert space representation of the algebra. The trace in a Hilbert space representation is infinite. The trace function is a sort of renormalized version of the trace in a representation with an infinite factor divided out. Well, that's an algebra of type 2. Instead, an algebra of type 1 does have an irreducible representation in a Hilbert space, and I'll call this Hilbert space H prime because it's not necessarily the same as the original Hilbert space H that we defined using the GNS construction. In this case, one can show that A is actually the algebra B of H prime of all bounded operators on H prime. There's then a natural trace, simply the trace in the Hilbert space H prime. If H prime is infinite dimensional, this trace is not defined on all elements of the algebra, since, for example, the trace of the identity is infinite. It's defined for a large subalgebra of, or even an ideal of matrices said to be operators said to be of trace class. For either type 1 or type 2, once there's a trace, one can define density matrices. If H is any Hilbert space representation of our algebra, either the minimal one that we started with, or maybe a bigger one that includes degrees of freedom beyond the horizon, and if psi is a state in this Hilbert space, then a density matrix is an operator rho that obeys the usual property that the expectation value of any element of the algebra O in the state psi is the trace of O times the density matrix. It's not hard to prove that such a rho always exists and is a positive element of, or in general, affiliated to the algebra. Moreover, if psi is normalized to 1, then the trace of rho, which is the trace of 1 times rho, is the expectation value of 1 in the state psi, and that's 1. So rho obeys the usual normalization condition of a density matrix that says the trace rho should equal 1. Once we have density matrices, we can define von Neumann entropies and other functions important in quantum information theory. So for example, the von Neumann entropy of a density matrix rho is minus trace rho log rho. However, there's an important difference between a type 2 algebra and a type 1 algebra. For a type 1 algebra, the trace can be defined literally as the trace in an irreducible representation. No renormalization is required, so the definition of the algebra is completely natural. For a type 2 algebra, there was an infinite renormalization in the definition of the trace, and this corresponds to an additive renormalization of the entropy. In fact, if the trace undergoes a multiplicative renormalization, like so, then to satisfy the definition of the density matrix, we rescale rho by the opposite factor, and the effect on the entropy is to shift it by plus log lambda. So the best we can say is that entropy in a type 2 algebra is defined up to an additive renormalization independent of the state. What are well defined are really entropy differences. That's analogous to entropy in classical physics. Entropy differences in classical physics can be defined by integrating the first law, but in classical physics there's no natural zero of entropy and no natural way to fix an overall additive constant. Actually, I think it would be fine to take questions now if there are any. We aren't quite so pressed for time as I was last time I gave this talk, so we could stop for questions.
Okay, if somebody has a question, they can write it in the chat quickly or raise the hand.
Let's see what's in the
Somebody
chat.
asked.
Well,
Somebody asked, can you explain the
somebody
infinite
can explain the
renormalization?
normalization. It's not well. What I would interpret the question to mean the following: can I explicitly construct a type 2 algebra for you? As I said, a type 2 algebra, in any type 2 algebra, any Hilbert space representation is reducible, and the trace in that representation is infinite. So it takes a renormalization to define a trace for a type 2 algebra. If you want to see how that renormalization works, the essence is you need an explicit description of a type 2 algebra, which I wasn't really planning to give today. I've given it in many previous occasions, including in some review articles I've written. Perhaps if perhaps I don't think I want to try to construct a type 2 algebra right now, and therefore I won't be able to demonstrate explicitly the renormalization. But intuitively, intuitively, any representation of the algebra is too big by an infinite factor. So you have to, you can make the representation smaller and smaller. It never becomes irreducible. And so a trace in a Hilbert space representation would be infinity times the trace you really want. And you have to divide out that infinite factor. When you do so, dividing by infinite factor always, or usually has an ambiguous additional finite factor you could divide by. And that's why there isn't a natural definition of the trace. Are there any other questions?
Yes, there is another one. Do type 1 and type 2 together give type 3?
No. So perhaps what the question intended was, if you take the tensor product of a type 1 and type 2 algebra, what type do you get? The answer is type 2. Think of type 1 as very special, type 2 is less special, type 3 is generic. If you take the tensor product of algebras of different types, the tensor product is of the highest type of any factor. So for example, a tensor product of type 2 and type 3 is of type 3.
Okay, great. I don't see any other question. Maybe we can continue.
So what do we expect for the algebra of observables accessible to an observer in quantum field theory with or without gravity? The interesting case is an observer who, because of black hole or cosmological horizons, cannot see the whole universe, or even a complete initial value hypersurface. This is, well, here I've given a Penrose diagram illustrating an example. This example is a geodesic observer in de Sitter space. One can choose coordinates, given any, de Sitter space has maximal symmetry, so any two geodesics are equivalent. And so any geodesic in de Sitter space is equivalent to the left boundary of the Penrose diagram, which I've chosen here as the observer world line. And recall that in a Penrose diagram, causal curves travel at most at a pi/4 angle from the vertical. So the two diagonal lines in the picture are the past and future horizons of the observer. And the portion of space-time that the observer can both see and influence is this green portion called a static patch. So what the observer can see in de Sitter space is precisely this green region. The time-like tube theorem of quantum field theory. Now I'll make a statement, no gravity here. This is for quantum field theory in a background de Sitter space. The time-like tube theorem says that the algebra of observables along the observer's world line is the same as the algebra of observables in the whole causal wedge shown in green. A heuristic explanation is what I've said here. The observer can shine a laser beam on any object in the static patch and see what bounces back, thereby learning the full contents of the static patch. Now, a classic result that goes back to Araki is that in quantum field theory without gravity, the algebra of a proper subregion of spacetime, any subregion that does not include a complete Cauchy hypersurface, is of type 3. The type 3 nature of the algebra of a region has a dual and ADS-CFT duality that was studied by Liu and Leuthäuser in papers that were influential. To give an example of their construction, what I've now drawn is the Penrose diagram for a pair of asymptotically anti-de Sitter black holes entangled in a thermofield double state. So in this example, the Penrose diagram has two vertical lines. Each vertical line represents an asymptotically anti-de Sitter boundary, conformal boundary of the spacetime. And we imagine an observer who lives in one of those boundaries, shown as the dark blue line. So in this duality, the conformal field theory, which is an ordinary theory without gravity, lives on the boundary of the universe. So here there are two boundaries, so two copies of the CFT, one here and one over here. So the light blue wedge is the region causally accessible to the right boundary, made in dark blue. In the approximation of treating the bulk theory as a quantum field theory in a fixed background, the algebra of the light blue region is of type 3, so in an appropriate limit, That's also the case for the algebra of observables on the right boundary. Now this might puzzle you slightly because on the whole right boundary, we simply have to find, or we could simply define a quantum field theory. And, well, okay. Well, let me explain here. When the boundary dual theory is, for example, an SUN gauge theory of some definite integer n, the thermofield double state is just a state in a tensor product of two copies of the Hilbert space of the boundary CFT. The algebra accessible to the observer on the right side is just B of HR, the type 1 algebra of all bounded operators on HR. That's a simple answer, but it has the drawback that for finite n, notions of spacetime and its causal structure are not precise, and it's difficult to formulate interesting puzzles about a black hole in a sharp way. Instead, in the large n limit above the Hawking page transition, the thermofield double state is a state in a connected spacetime. It's also a state in a Hilbert space that's not a simple tensor product. It's a state in what is sometimes called the thermofield double Hilbert space. That's a Hilbert space that contains the thermofield double state, but above the Hawking page transition, it's not a simple tensor product. So the causal wedge of the boundary in this connected spacetime is this light blue region here. It's a subregion whose operator algebra in ordinary quantum field theory is type 3. So even though for finite n the right boundary would have a type 1 algebra, in the large n limit it must be possible to define an emergent type 3 algebra. To define this emergent algebra, Liu and Lothheiser considered single trace operators normalized as, for example, the trace of f mu nu, with no additional factors of n. For finite n, these operators are expected to generate the type 1 algebra of the boundary conformal field theory. In the large n limit, they have divergent expectation values. So to get operators with a large n limit, Liu and Lothheiser subtracted their expectation values at some inverse temperature beta above the Hawking page transition, and considered subtracted operators O prime that do have large n limits in a thermofield double Hilbert space to find at that value of beta. The algebra they considered was the von Neumann algebra generated by these subtracted operators O prime in the large n limit. ADS-CFT says that this algebra is of type 3, since it's the same as the bulk algebra of the causal wedge, treated as an ordinary quantum field theory in the limit that Newton's constant g vanishes. So the emergent type 3 algebra generated by these operators O prime is simply dual to the type 3 algebra that Araki would have defined for the light blue region of the bulk theory. An important detail is that the large n algebra of single trace operators, defined this way, does not contain the Hamiltonian h. Keeping track of powers of n, you find that it contains not h but h divided by n, which in the large n limit is not 0 but is central. So in the large n limit, the generator of time translations is not contained in the algebra. Time translations are an outer automorphism of the algebra. I'll come back to that later, but for now I just note, following Liu and Lothheiser, that it means that in the large n limit, the operators in a time band are a proper subalgebra. So for example, consider, I've drawn in dark blue just part of the boundary. And we imagine defining an algebra for that region. If that algebra included the Hamiltonian, you could use conjugation by e to the minus iht, conjugation by the exponential of the Hamiltonian, to move operators forwards and backwards in time. So you would not be able to define a subalgebra for only part of the boundary if the subalgebra was supposed to contain the Hamiltonian. But the large n limit this way is such that the algebra does not contain the Hamiltonian, and you can define an algebra for just part of the boundary. And that algebra, in fact, is simply the algebra in the bulk of the causal domain of this blue region, the algebra that you can both see and influence from within this limited part of the boundary. Now, various properties of the bulk geometry and dynamics are reflected in properties of these emergent algebras. I'm going to mention a few papers, but I won't explain a lot of details. We've already seen that the connectedness of the two sides of the thermofield double is reflected in the fact that a certain emergent boundary algebra in the large N limit is of type 3. Engelhard and Liu discussed an analogous algebraic signal for quantum connectedness between a black hole that's been evaporating for a long time and its radiation. Then Gesto and Liu argued that by considering subalgebras of time bands, you can give a criterion for existence of sharp horizons in the large N limit, even in the Stringy case, that is, even when G squared N is kept fixed as N goes to infinity. This is non-trivial because we know that horizons exist in field theory, but it's a little bit less obvious that horizons can be defined in string theory. And this argument, based on the properties of the algebras, indicates that they can be. And then there's additional work I've cited here for more on algebras associated to time bands and stringy geometry. Now, this story changes if we consider a slightly different large N limit that does include the Hamiltonian. But before explaining that, I want to explain some heuristic reasons to expect that type 2 algebras should be relevant to semi-classical gravity. In this context, semi-classical gravity probably means any gravity in any situation in which classical concepts of causality make sense. The basic reason one might think that type 2 algebras are relevant to gravity is that in gravity we can define entropies even when we cannot define quantum mechanical microstates. A quantum theory with entropies but no microstates is a good candidate to be described by a type 2 algebra. So Bekenstein and Hawking defined the entropy of a black hole. We can define it, it's defined from the area, but it's defined with no knowledge about microstates, which is consistent with the idea that this entropy could be perhaps understood in a type 2 algebra. Somewhat more specifically, in gravity we often compute by path integrals, quantities that we give names like trace e to the minus beta h, or more generally traces of more complicated operators, even when we don't have a Hilbert space H and operators on it, such that the quantities we compute really are such traces. So we routinely and commonly define certain functions to be traces, even though they aren't traces in any sense we know. We call these functions traces. Why? Well, first, they satisfy the two conditions that define a trace. One is that the trace of O prime O equals the trace of O prime. The other is that the trace of O dagger is positive. And typically, we believe that we are computing large N limits or asymptotics of functions that really would be traces for positive integer n. Well, but in large N limit, what do these formulas mean? One might suspect that objects that have general properties of traces but that aren't actually traces can be interpreted as elements of a type 2 algebra whose trace function is what I'm calling TR trace. An example that can be made very explicit is JT gravity coupled to matter in spacetime dimension 2. We refer to the objects we compute from disk path integrals as traces, even though there is no one-sided Hilbert space in which they are traces. An interpretation is that objects such as e to the minus beta h and so on are elements of an algebra of type 2 infinity in which the trace function is computed by a path integral on the disk. Well, what's this good for other than hanging a plaque on the wall and declaring we found a type 2 algebra? One answer is that although JT gravity does not have a one-sided Hilbert space describing states of a single black hole, it does have a two-sided Hilbert space describing states of a pair of entangled black holes. In this situation, we define type 2 algebras, A left and A right, for the right and left boundaries, respectively. One can show that they're each factor as trivial center and are each other's commutants. The statement that they are commutants means that even though there can be a long wormhole that classically is out of view for an observer on either side, with a lot of matter inside the wormhole, the combined algebra contains all operators in the full Hilbert space, with no gaps. So classically, an observer on the left would only see this little wedge, and an observer on the right only sees this little wedge. But somehow, if you combine the algebras A left and A right, they see everything. For example, the normalized length between the two sides, which is a typical operator that can't be measured from just one side, is an operator in the tensor product Hilbert space, tensor product algebra. That's a sort of non-perturbative version of entanglement wedge reconstruction. There's a gap between the left and right causal wedges, but there's no gap between the reconstructible wedges by observers on the left and right. There's also no known classical geometric description of those reconstructible wedges in general, except in the usual sort of semi-classical limit. It's not clear in what sense one might hope for such a description. This has an interesting variant in n equals 2 supersymmetric JT gravity. In the long wormhole situation, in bosonic JT gravity, with any amount of matter in the bulk, the energies E left and E right measured on left and right can be arbitrarily small, but not strictly zero. But in n equals 2 JT gravity coupled to matter, no matter how much or what matter there's in the bulk, there's a state that, to a boundary observer on left or right, looks like a supersymmetric ground state with zero energy. In other words, it's an extremal black hole. So there's a large space of two-sided extremal black holes, one for each primary field of the matter system. Projecting the type 2 infinity algebra on this space of ground states gives a type 2-1 algebra that acts on extremal black holes. In space-time dimension bigger than 2, in theories of ADS gravity with a known conformal field theory dual, we expect that for positive integer n, a one-sided Hilbert space Hn exists, which at high enough energies is a black hole Hilbert space, though we don't understand it very precisely. So we expect quantities like these really are traces if n is a positive integer. However, if we compute these functions in an asymptotic expansion around n equals infinity, we get answers that we cannot literally interpret as Hilbert space traces. In fact, the Hilbert space Hn of the theory with integer n does not have a large n limit. What we do have, apparently, in an asymptotic expansion near n equals infinity is a description by a type 2 algebra. Why is that limit important? Presumably it's important because that's the realm of semi-classical notions of causality, which are tied to conceptual questions about black holes and quantum cosmology. Now, JT gravity in 2 dimensions is a little different from what I'm describing here because of a few facts. First, the analog of n is the number C of matter fields, and no large C limit is needed to define a type 2 algebra. And this is related to the fact that even for fixed C, there's no one-sided Hilbert space. Above 2 dimensions, we don't get a close analog of JT gravity in theories where we do know the boundary dual. But you could consider a bottom-up theory of gravity that potentially lacks an ultraviolet completion, like pure Einstein gravity or Einstein gravity with a few matter fields, and likewise potentially lacking a well-defined one-sided black hole Hilbert space. In such a case, one could compute trace e to the minus beta h by Euclidean path integrals. One could expect to give the results a type 2 interpretation, at least perturbatively or to the extent that the theory makes sense, even if the theory in question does not really have a well-defined black hole Hilbert space. Another way to say the same thing is that to have a continuous spectrum, which a black hole has in any approximation that we actually understand, and which certainly has semi-classically, but a finite partition function trace e to the minus beta h, such as we also compute, is not possible if trace is literally the trace of an operator in Hilbert space. But it's perfectly possible if e to the minus beta h is an element of a type 2 algebra, and trace is the trace of this algebra. Now, I'm going to spend a little time for a case in which we can be more explicit about constructing the type 2 algebra. So the first example was a two-sided Schwarzschild black hole, but there's also an example in cosmology, which I think I'll explain. So here I've drawn, again, the Penrose diagram of a two-sided asymptotically anti-de Sitter black hole. So it's the same picture we had before. Well, when we had it before, I emphasized an observer living on one side and only being able to see the region outside the horizon. So the picture is the same as this one, but I'm adding to it a couple of things. One is I've drawn an initial value hypersurface at time 0 that cuts from left to right through the picture. But two, very importantly, this picture does have time translation symmetry. And I want to add back the Hamiltonian in the construction of Lewin Lighthizer. So I want to take account of the time translation symmetry. But as you may know if you've studied the Kruskal-Szekeres coordinates for a black hole, for a two-sided black hole, time translation symmetry goes oppositely on opposite sides. So the time translation symmetry moves forward in time on the right and backward in time on the left. Or if you reverse its sign, it will do the opposite. It's forward in time on one side, backward in time on the other. The Hamiltonian can be written as an integral over an initial value surface S, which I took to be this one, the horizontal line. And we can take it to be a t equals 0 where t is Schwarzschild time. So the Hamiltonian, in the limit that gravity is turned off, is just the integral over S of the stress tensor times the vector field that generates time translations. In heuristic arguments, we can decompose S as a union of portions S right and S left to the right and left of the horizon. And then we write the Hamiltonian as H right minus H left, where H right and H left are integrals on S right and S left. I include a minus sign in H left because since the vector field V goes backwards in time on the left, a minus sign ensures that H left and H right both go forwards in time. In ordinary quantum field, so that with splitting the integral as two pieces, you'd have that H is H right minus H left. In ordinary quantum field theory, decomposition that H is H right minus H left is not actually correct. If you try to make that decomposition, you get ultraviolet divergences at the bifurcation surface at which S right and H left meet. The bifurcation surface is the surface where the horizons meet. In this Penrose diagram, it's a point, but in space-time, it's a two-sphere in 4 dimensions, because each point in the Penrose diagram represents a two-sphere. In gravity, there's no problem with the decomposition that H is H right minus H left. This is just the ADM expression for the total conserved charge H in terms of ADM energies H right and H left, measured on the right and left boundaries. Now let's try to describe an algebra of observables accessible to an observer who lives in the asymptotically ADS region U right on the right of the bifurcation surface. In ordinary quantum field theory, and with linearized gravity treated as just one more quantum field, the algebra of observables in region U right, the dark blue region here, is an algebra A0 of type 3. But in the presence of gravity, the full algebra A of observables has one more generator, H right. So A equals A0 H right is the von Neumann algebra generated by A0 together with bounded functions of H right. Remember, H right is just the ADM mass on the right side. While H right is observable for an observer in the right region U right, the corresponding left energy, H left, commutes with all observables on the right. Taking the perspective of an observer in region U right, who knows nothing about H left, let's just call that operator X, where the uninformative name is meant to symbolize the fact that the observer we're studying knows nothing about what that operator represents. We can trivially write the formula that H is H right minus H left, or in other words, H right minus X, in the form H right is H plus X. So taking into account, we can describe the observable algebra in region U right. It's generated by what we would have in quantum field theory, plus one more operator, which is the ADM mass on the right side, but that's the same as H plus X. What we've run into here is a classic construction of a type 2 algebra starting with a type 3 algebra. The cross product of an algebra A0 by one parameter group with generator H is defined by joining to A0 one more generator H plus X where X is central. So we get what we've just found, the algebra A generated by the quantum field operator algebra plus the one more operator H plus X. This construction can be defined for any automorphism of a von Neumann algebra, but if the symmetry is the modular automorphism group for some state, which is the case for the black hole with symmetry generator H, I should have said Bosoniano and Wickman as interpreted by Sewell. And if in addition the initial algebra is of type 3, also true here according to Araki, then the cross product algebra is type 2 infinity. If A naught acts on a Hilbert space H naught, which was simply the bulk Hilbert space without gravity, H is an operator in H naught, then the cross product algebra acts on a Hilbert space that's slightly extended by including functions of X. So it acts on H naught tensored with the Hilbert space of functions of X. The trace in the cross product algebra is as follows. If psi TFD is the thermofield double state in the starting Hilbert space, and psi hat is defined as psi TFD times e to the x over 2, then the trace is just the excitation value in the state psi hat for any operator in the algebra. This algebra is of type 2 infinity, not type 2, 1, since the trace of the identity is given by the integral of e to the x dx, which diverges. Since we have a trace, we can define an entropy. To compare this entropy to the usual generalized entropy, we have to remember that the generalized entropy is defined for quantum fields in some state psi in an almost definite spacetime. In our case, to get a definite spacetime, we need the canonical conjugate to x, which is a relative time shift between left and right boundaries, to have an almost definite value. This means that to be able to compare to the generalized entropy, we could consider states such as this one, where the function f of x is slowly varying. In this paper, we considered the density matrix of such a state. We computed approximately the density matrix of such a state and shown the entropy agrees with the usual generalized entropy up to an important additive constant independent of the state, which is undefined from this point of view. Subsequently, the exact density matrix was computed for states without assuming f is slowly varying in this paper. In general, it's hard to use this to compute the entropy when f is not slowly varying, but this was recently done for a class of states far from semi-classical, in which x rather than its canonical conjugate has an almost definite value, so the generalized entropy formula does not apply. In this construction, it's important that the two-sided ADS Schwarzschild black hole has an equilibrium state, the thermofield double state. In important examples such as a Kerr black hole or a Schwarzschild de Sitter spacetime, there's no equilibrium state, and the discussion as presented does not apply. However, by starting instead with the unrest state and operators on the past horizon, you can somewhat similarly make a type 2 infinity algebra for these spacetimes. And that's also been generalized to cosmology. What I've explained for black holes has an analog for de Sitter space that I actually think is more interesting because de Sitter entropy has been even more mysterious than black hole entropy. Cosmological horizons, such as the horizons of de Sitter space, are highly observer dependent. They bound the portions of spacetime that a given observer can see or influence. For example, consider an observer propagating on a geodesic gamma in de Sitter. As already said, we can choose coordinates such that gamma is the left boundary of the Penrose diagram. And the green region P, called a static patch, is the region causally accessible to the observer. In ordinary quantum field theory, we associate to P an algebra of observables A naught, which is of type 3. In gravity, we first observe that the region P is invariant under a one-parameter group of time translations, whose generator I will call H. So these time translations literally act as time translations along the observer world line. They move the observer's proper time forwards in time. On the opposite boundary, they would move the proper time backwards in time. What they do elsewhere is more complicated, but they do generate a symmetry of the region P. In fact, they have to, since they generate a symmetry of the observer's world line. Inevitably, they generate a symmetry of the region causally accessible to the observer. Because de Sitter space is a closed universe in the presence of gravity, H has to be treated as a constraint operator. That means that only H-invariant operators are allowed, so naively we should replace A naught with the H-invariant subalgebra A naught H. However, this does not work. A basic result in ergodic theory, using the fact that H generates the modular automorphism group for a certain state, says that A naught H consists only of C numbers. To get a sensible answer, we need to take seriously the fact that the reason we're interested in the static patch P is there's an observer in that patch. We're trying to discuss the measurements accessible to that observer. We need to include this observer and the observer's Hamiltonian in the description of the algebra and the constraints. For a simple model of the observer Hamiltonian, we take a constant mc squared plus q, where m is the observer's rest mass, and q is the Hamiltonian for the experimental apparatus the observer carries. If m is really to be the observer's rest mass, we want q non-negative, but otherwise we give q a continuous non-degenerate spectrum. So the Hilbert space of the observer is L2 of q, where q is non-negative. For a moment, though, I will ignore the fact that q is supposed to be non-negative and freely use the conjugate operator p equals minus id by dq. Naively, well, okay, now we want to construct the algebra accessible to the observer. Well, naively, we've got all the quantum field operators not involving the observer's Hilbert space, together with q and p that act on the observer's Hilbert space. So the naive algebra generated, including the observer, is then A1 generated by A naught together with P and Q. However, we have to impose the constraints. The constraint generator now receives a contribution from the observer Hamiltonian and is H hat equals H plus the observer Hamiltonian. The H hat invariant subalgebra of A1 is not quite non-trivial. It's generated by dressed operators e to the IPH A, e to the minus IPH for all A, together with one more operator Q. So A1H, sorry, this is a misprint. That H should be this H hat. The H hat invariant part of A1 is generated by these operators. By conjugating with e to the minus IPH, one can show that A1H is isomorphic to the cross product algebra as defined earlier. In particular, it's again of type 2 infinity. But we have to take into account the constraint that Q is non-negative. If pi is the projection operator onto non-negative Q, the algebra we want is really this one, or at least I have the right font, but I left off the hat from H. So the algebra we want is this one, but with pi, projecting before and after with pi. That last projection turns the type 2 infinity algebra A1H into a type 2-1 algebra. It means, therefore, that there's a state of maximum entropy, which is the maximally mixed state with density matrix 1. Concretely, the maximum entropy state is simply de Sitter space with the observer in thermal equilibrium. This was guessed long ago on purely thermodynamic grounds, with no microscopic definition of entropy, and without explicitly including an observer. So what we've gained is that now we do have a microscopic definition of entropy, but giving one required us to include an observer, and the presence of the observer is the rationale for studying the static patch we were studying. So, well, the observer, including the observer explicitly, makes the physics make more sense and mathematically enables us to define the entropy. If we want to go beyond lowest order in G, it won't work well to say that we're trying to define operators in the causal domain of the observer, because this fluctuates quantum mechanically and isn't really well defined except in the classical limit. So an operator doesn't know whether it's inside the static patch or not, because the static patch, the observer's causal domain is fluctuating, so it wouldn't be clear what really are operators that are inside the causal domain. If you try to define a bulk operator, it'll have some probability to be inside and some probability to be outside of the causal domain. What's equivalent in leading order in G, where we were working so far, and makes sense in higher orders, and really is a better match for the idea of the algebra accessible to the observer, is to take for the naive algebra A0 that we started with, not the algebra of all operators in the static patch, but simply the algebra of all operators along the observer's world line. That way we get a version that appears to make sense at least to all orders in perturbation theory in G. Moreover, it can be defined universally, with no a priori knowledge of the spacetime in which the observer is living. In other words, this gives a background-independent algebra that's determined by the theory, with no knowledge required about the spacetime. Different spacetimes and different observer trajectories in the same spacetime correspond to different representations of this one universal algebra. Now I'm going to close this talk with a speculation. Can we improve the definition of entropy I've given so there will be no arbitrary additive constant? We can possibly do this by thinking of the Hartle-Hawking no-boundary state, psi HH, as a universal state of maximum entropy. I assume this state makes sense as a state of the observer algebra, no matter what spacetime the observer is living in. If so, then given any other state psi of the background-independent algebra, we can define the entropy S of psi to be the relative entropy S of psi relative to psi HH. The state psi HH has been interpreted previously as a universal state of maximum entropy. You can find a review in this article and also a critique. And a similar definition of entropy was used previously in proving a version of the generalized second law. But at the moment, there's only very limited evidence for this proposal. The main problem with the proposal to me, well, one problem is that we don't understand the state psi HH well enough to do very much with this proposal. But for this to be a sensible definition of entropy, psi HH should be what's called a tracial state, a state such that the expectation value in psi HH is the trace of the algebra. And although that can be justified in de Sitter space, that's the only case where that's been justified. So if you could convincingly show that psi HH is a tracial state, then this proposal would actually be a rather attractive proposal as a universal definition of entropy in quantum cosmology with no arbitrary additive constant. But we're far away from that. I have no idea why it would be true in general that psi HH is a tracial state. At any rate, these are the thoughts I have to offer today. Thank you very much for your attention.
Great, thank you very much. Let's thanks Edward for this very nice overview. Was very nice.
So we could have questions now, if there are
Yeah,
questions.
sure. I'm just waiting for the people to write the questions. Do you prefer to read them yourself, or I should read it to you?
Well, you can, I'll read them myself if they're in the chat. But there aren't any new questions. Oh, there are.
Yeah,
Some.
there are many.
Okay. Why is it not necessarily the same? Okay. Well, okay, we defined a Hilbert space using the GNS construction. And then I think the question was asked. Okay, that Hilbert space is not guaranteed to be an irreducible representation. So at the point in the talk when I said that a certain Hilbert space was not necessarily the same as the GNS Hilbert space, that Hilbert space that I called H prime was supposed to be an irreducible representation, whereas nothing guaranteed that H was irreducible. And you wouldn't really expect the GNS Hilbert space to be irreducible. It's usually not going to be irreducible. What is true, though, for a type 1 algebra is that every representation is a direct sum of, or direct integral of copies of an irreducible one. So although the irreducible one wasn't the same as the GNS Hilbert space, the GNS Hilbert space was equivalent to many copies of it, many copies of the irreducible one. Next question, is A1H a collection of dressed observables where the A0 observables are dressed to the observer? That's correct, except that there's one more generator, which was the observer Hamiltonian. So in the situation you were asking about, A1H consists of dressed observables. I just didn't use the phrase dressed observables, but I defined them. But there was one more operator. It's important to have one more operator because, well, you don't get this nice factor without including that operator. Well, anyway, it's unnatural to not let the observer measure the observer's Hamiltonian. So in the black hole case, the one more operator was the ADM mass. In the de Sitter case, the one more operator was the observer's Hamiltonian. Those one more operators were very important. Bow and gel. The question is, when we turned on gravity to make type 3 into type 2, were we making gravity dynamical? Well, just barely. We were including a little bit of information from gravity. In the black hole case, we included the ADM mass. And in the de Sitter case, we took into account that the symmetry generator of de Sitter space, because de Sitter space is a closed universe, has to be treated as a constraint. So the ability to measure the ADM mass, and also the fact that the symmetry is a constraint operator, those are facets of gravity. So we just barely took a little bit of gravity into account, and a little bit of gravity was enough to turn type 3 into type 2. I'm afraid we won't have as easy a time in understanding how type 2 is related to type 1.
Can you elaborate more on that? What is not gonna be easy? What do you think is not gonna be
Well,
easy?
I can't
Or
guarantee it easy. It looks difficult. Maybe somebody will show it is easy. I don't know how to. Well, I don't know what to say about the bulk theory when n is a definite integer. So when n is a definite integer, the boundary algebra is of type 1, but we don't have any insight about the bulk theory. I suspect that, well, I don't know. Well, I think we're far away from knowing in what sense the bulk theory is well defined when n is a definite integer. Okay. Anyway, I doubt type 2 will be converted to type 1 by simple semi-classical reasoning. The next question looks a little bit technical. So the question is about the following. A certain index calculation is indeed a counting of states for finite n. But if you try to take the large n limit, the large n limit of the answer makes sense. But I think the question is, okay. So, well, I'm not going to be able to answer this question. The question is about a situation where for finite n, you can do an index calculation and you get an integer answer. In the large n, then the answer has an asymptotic behavior for large n that you can compute by matrix model methods and large n saddle points and so on. But the answer is hard to interpret in terms of a trace in a Hilbert space. I expect the answer is that for any integer n, you have a Hilbert space and you're counting states. But when you write asymptotic formulas near n equals infinity, I think they're more like type 2 formulas than state counting. The next question is, has something interesting been done with care? Maybe I'll answer for ADS. For ADS, you can consider the observer to live at spatial infinity, where the CFT is defined. And we anyway assume ADS is a case that you can probe from outside. We usually take the point of view of an external observer who can probe ADS from outside by measuring the operators of the dual CFT. And therefore, in ADS, we don't really need to explicitly include an observer. And that's true for the black hole Schwarzschild or Kerr. In an asymptotically flat or asymptotically ADS black hole, we can consider the observer to be living at infinity, looking at it from outside. And I think explicitly including the observer will not add much. I think it's mainly in a closed universe, like de Sitter space, that to make sensible statements you need to include an observer. And there's recent papers discussing a different aspect of that, which is that, well, I wouldn't say this is very well understood and well established, but there are arguments suggesting that in non-perturbative quantum gravity, the Hilbert space of a closed universe is one-dimensional, meaning that you can't say anything sensible about observations in a closed universe unless you explicitly include an observer, as done in some recent papers. When we consider baby universe topologies beyond semi-classical, we'll change the type 2 into a type 1. My guess is that that won't be enough. I think that, well, I'm not sure what you mean by beyond semi-classical. If beyond semi-classical means for a definite integer n, then yes, that's what should turn the type 2 into type 1. But it might be very hard to understand in terms of baby universes. Next question. What's requirements for boundary CFT when taking bulk theory G to 0? Well, usually if we keep G squared fixed and take G squared n to infinity, then we get the bulk theory at in the limit that G goes to 0 and n was going to infinity. Next question. It seems like the observer in de Sitter was an eternal observer. This is a valid criticism. So one would like to improve the discussion for an observer who does not exist for all times. Possibly an observer who didn't exist far in the past. Even an observer who's one-sided toward the future. After all, we didn't always exist. So if you want a model of us, you should consider an observer that didn't always exist in the past. And unfortunately, I imagine we won't always exist in the future either. But anyway, it would certainly be an improvement to get a good model for an observer that doesn't exist for all times. I've been unsuccessful in trying to do so, but I recommend the problem. Can the linearity of the algebra be affected by interactions with matter? It's important to take in account interactions between gravity and matter to define the algebra. But in the framework I was using, we assumed that we had states and operators acting on them. So the algebra acted linearly on the state space. Getting away from that would be a more drastic departure from quantum mechanics. I was including a certain amount of quantum mechanics, which I stated at the beginning what I wanted to keep. Okay, the last question, at least so far, is what's my advice about proceeding with a theoretical physics career? I can only give rather lame advice. Learn all you can when you're young and take advantage of opportunities. So, okay, there aren't any more questions, at least at the moment, but we can give everyone another chance to ask another question.
Sure. If somebody wants to ask something else, go ahead. There is another question.
Should we be worried about the observer Hamiltonian being unbounded below? Well, we shouldn't expect the observer Hamiltonian to be unbounded below. Our Hamiltonian is bounded below. It's stable. So it's a better model of the observer to assume the Hamiltonian is bounded below. I think what we should be asking is how can we improve the model further? For example, as suggested by one of the questions, by taking into account the fact that the observer wasn't really eternal. And actually, in one of my papers, I showed that you can improve the observer. You can improve the model by just assuming the Hamiltonian is bounded above as well as below. That gives a rather crude way to incorporate the fact that the observer can't really measure everything. So I don't see more questions, so maybe this is a good time to call it a day.